many different vendors to choose from when buying robot parts, such as Vex, AndyMark, or West Coast products. For Team 268, we mainly use Vex Pro parts, so a lot of the materials I'll be going over in this lesson will actually be from Vex. So the main structural component of a robot is stock, which is just aluminum pieces that are put together to form the skeleton of the robot. There are many different types of stock, such as square stock, which is stock in the shape of a square tube that's 1 inch by 1 inch. There's also 1 by 2 stock, which is stock in a rectangular tube that's 1 inch by 2 inch. There's flat stock, which is a flat strip of aluminum with a little width of 1 inch. And there's also L stock, which is aluminum in the shape of an L. Now, if you take a look at our FRC robot, you'll notice that a lot of the robot is made up of stock, because stock forms the structural basis of all of the robot's mechanisms. For instance, you can see here there's a piece of 1 by 1 or square stock. There's a lot of 1 by 2 stock for this arm pivot. And up here, there's more 1 by 2 stock. And you'll also notice that there are some pieces of flat stock here. To connect stock together, we use gussets, which are pieces of aluminum that can get bolted to 2 or more different pieces of stock to form a connection. You'll notice that these little holes in the gusset line up with the holes on the stock so that bolted connections can be made. There are many different types of gussets which serve different purposes. This is a L gusset, or a 90-degree angle gusset, and this serves to connect 2 pieces of stock at a 90-degree angle. Head over to our robot, you'll notice that these 2 stocks are connected at a right angle by this gusset, by this L gusset. Angle gussets can come in a variety of angles, anywhere from 30 to 150 degrees. This, for instance, is an angle gusset that is 60 degrees, and it connects 2 pieces of stock at a 60-degree angle, while this 120-degree angle gusset connects 2 pieces of stock at a 120-degree angle. Other structural gussets include T-gussets, which connect stock to form a T. This is a short T-gusset, and this is a long T-gusset. And you'll notice on the final robot, T-gussets are used in the drivetrain to connect stock to form a little T shape. A corner gusset, like a 90-degree angle gusset or L gusset, allows structural components to be connected at a right angle. In addition, this little hole here serves as a hole for bearings, which we'll go over. You'll notice on the final robot, for instance, in this area, these 2 stocks had no room to have a L gusset fit on top of them because of this, so a corner gusset was used to connect them, since these holes were facing inward. In addition, the surface that the corner gusset provides, along with the little holes, allow other robotic components to be mounted on the corner gusset. For instance, over here you'll notice that the pneumatic compressor was mounted on the corner gusset. Some gussets are also just dedicated to housing rotating components, mainly bearings. You'll notice that this hole in this end bearing gusset is similar to the hole in the corner gusset. And if you head over to the final robot, you'll notice over here, this shaft with all these green wheels has been mounted to the end bearing gusset, which is mounted at the end of a square stock. A side bearing gusset is similar to an end bearing gusset in that it houses a bearing in its big hole, except that it mounts on the stock such that the bearing would come off the side of the stock. So over here, instead of the bearing and shaft setup coming off the end of the stock, for a side bearing mount, it would come off the side. There are also gussets that are dedicated to mounting motors. For instance, this Versaplanetary side mount gusset mounts a motor on this face, and these little parts of the gusset hook onto a stock. So over here in our final robot, you'll notice that the motor here is attached to this piece of stock using a versaplanetary side mount gusset, which has its little tabs hook on to the holes of the stock. There's also a versaplanetary parallel mount gusset, which also mounts motors to stock, except that the motor goes in such that it runs parallel to the stock. You'll notice here this little hole is for the output shaft of the motor to stick through. So, for instance, on our final robot over here, you'll see the versaplanetary parallel mount gusset with the motor running parallel to the stock that the gusset is mounted on. Hex shafts are the axles of any rotating parts of your robot. In FRC, hex shafts are commonly used due to the fact that a hex shaft, when used with a hex hole, doesn't require any locking mechanism. So you see here I have a wheel with a hex hole, and if I put it with this hex shaft, you'll notice that because the holes fit right with the shaft, when this axle spins, the wheel will spin right with it without the need for any locking mechanism if the hole and the shaft were circular. So you'll notice on our final robot assembly, hex shaft is used right here to form the axle of this rotating wheel component. And one more thing to mention is that this hex shaft is actually a half-inch hex shaft because the distance between two faces of the hexagon is roughly half an inch. And there's also a 3/8 inch hex shaft, which would have that distance being about 3/8 of an inch. But generally speaking, half-inch hex shaft is used more often on Team 263. So spacers are basically pieces that separate two other parts by a certain separation distance. Say, for instance, this is a half-inch spacer, so it would separate two pieces by half an inch. This is a 1/4 inch spacer, and this is a 1/16 of an inch spacer. So mainly for FRC, hex spacers are used. You'll notice that this spacer has a hex hole, and they're used on hex shaft to separate items on the shaft by a certain distance. So if you head over to the final robot, you'll notice that these wheels have spacers in between them so that they don't slide along and get closer or farther away from each other. They stay in place because these hex spacers kind of lock them in place by a certain. So bearings are components that sit in a hole and house a shaft in here, and they basically reduce the friction between the shaft, which spins, relative to the hole, because a bearing is really composed of two parts: the inner part, which can spin freely relative to the outer part. You'll notice in this diagram of a bearing taken apart that the inside component is separate from the outside component, and they're separated by a bunch of balls, which allows the inner ring to spin really easily. And when you put a shaft through this, and you put the entire bearing in a hole, the shaft can spin really easily because of the reduced friction because of all these balls. Now the most common bearing we use on Team 263 is the flanged hex bearing, which, as you'll notice, there is a half-inch hex hole here, and the bearing is flanged, meaning that it has a little lip here that goes around the outside so that when this bearing is placed in a hole, the lip catches the surface of the hole so that the bearing doesn't fall all the way through. On the final robot, you'll notice by this end mount gusset, underneath this black component, there is a bearing here, and there's also a bearing on the other side over here. And the hex shaft sits inside the bearing, and it can rotate with much less friction because of the bearing. There are also bearings that don't have a hex hole. For instance, this bearing has a 3/8 inch diameter regular hole, and there are also bearings that don't even have a flange, such as this bearing. You'll notice that it no longer has the lip that is the flange of the bearing. But most commonly used on our team is this flanged half-inch. Lock collars are little rings that sit on a shaft, and when tightened, they do not slide. So you can imagine that they can be used to sit on shafts and surround other components on the shaft, and when tightened, they'll lock those components in place and prevent them from sliding. There is a hex lock collar, which has a hex hole and sits on hex shaft. There's also a round lock collar, which sits on round shaft, but most commonly for FRC Team 263, we use hex shaft lock collar. And you'll notice on the final robot, this shaft is surrounded by a lock collar on this side, as well as a lock collar on this side, so that the shaft doesn't slide out of the gussets that way. It's locked in place so that everything stays put. Couplers are used to connect or couple two hex shafts together. And you'll notice that on the side there are these screws here, and when you tighten these screws, the coupler can lock onto two hex shafts. So if you notice, I have a motor here with a hex shaft, and I have another hex shaft. I can stick part of the hex shaft into the coupler and the other hex shaft into the coupler, and when I tighten these screws, the coupler bites down on both of these hex shafts, and by doing that, this shaft is now extended in a way, because these two shafts are connected by this coupler. Hubs are components that connect shafts to a bigger component so that the bigger component rotates with the shaft. You'll notice that this hub in particular has a hex hole for a hex shaft, and it has these mounting holes that can connect to a bigger component so that everything rotates together. This is also another hex hub. And over here you can see that this hex shaft connects to the hub, which connects to this yo-yo looking component, so that the entire yo-yo looking component rotates when the hex shaft rotates because of this hub. Gears transfer rotation along different parts of the robot, and gears are placed on shafts, and their teeth are supposed to mesh with other gears to transfer rotation. And one thing to mention is that gears are identified by the number of teeth that they have. So, for instance, this is a 24-tooth gear, and this is a 50-tooth gear. And on a robot, you can see that gears are used to transfer the rotational movement of this motor to the rotational movement of this arm. And you can see here on the robot that gears are used to transfer the rotation of the motor to the rotation of this arm. Another good thing to mention is that gears mesh together will reverse in opposite directions. So for this motor, when it spins, let's say it spins clockwise, then this arm will rotate counterclockwise. Motors turn electrical energy into rotational movement. So for this motor, the electricity comes into these two wire terminals, and the motor turns that electricity into the rotational movement of this output shaft. There are many different types of motors that you'll be using in FRC. This is a sim motor, which is one of the bigger motors you'll use for any situation where you need a lot of torque or rotational force. This is a mini sim motor, and this is a bag motor, and those are used for situations where you need less torque or rotational force. This is a 775 motor, which is smaller than a sim. You can see on our robot that there are motors everywhere because they power a lot of the mechanisms and a lot of the movement on the robot. Down here, you have many sim motors, which are used for the drivetrain, which drives the heavy robot around, and robots are also used. On our mechanisms, for instance here, the motor powers the rotation of these intake wheels. Back here, the motor powers the rotation of this arm. A gearbox is a system of connected gears that can modify the torque or rotational force as well as the rotational speed between an input and output shaft. So generally speaking, the input would be the rotation of a motor shaft, and the output would be the shaft that connects to the rest of your mechanism. In using a gearbox, you can kind of make a motor more powerful, or you can make it spin faster. There are many different types of gearboxes used for different situations. This, for instance, is a drive gearbox, which uses 2 motors and a really big gearbox. And this is used on the drivetrain of the robot. Since the robot is very heavy, a lot of power is needed to make the robot move around. This is a planetary gearbox, which is a smaller gearbox, and it's used to power a lot of mechanisms for less that don't require a lot of torque. Here on the robot, you can see that gearboxes are used all over the place. As I mentioned, the drivetrain uses a gearbox because the robot is very heavy, so a lot of power is needed to move the robot around. Additionally, a gearbox is used here to make these intake wheels spin at a certain power as well as speed. And a gearbox is also used here. It's very rare in FRC that you'll have a motor operating without a gearbox. Sprockets are similar to gears in that they transfer rotational movement, except unlike gears, their teeth do not mesh together. Instead, sprockets work with chains to transfer rotational movement. If you look at our final robot, you'll notice on the drive base, there is a sprocket system with chains, which is represented in gray, and they transfer the rotational motion of the center shaft, which is created by the motor. They transfer the rotational motion of that center shaft to the other wheels on the ends, so that when the center shaft spins, the other wheels also spin. Now there are different types of sprockets for the different types of chains. There's a 35 sprocket for a 35 chain, which is a thicker chain, and there's a 25 sprocket, which is for 25 chain, which is a thinner type of chain. And like gears, sprockets are named by the number of teeth. So this, for instance, is a 16-tooth sprocket. Belt and pulley systems are similar to chain and sprocket systems in that rotation is transferred along different parts of mechanism. And unlike gears, the pulleys do not have to mesh together. Now, in a belt and pulley system, the belt is usually a band of rubber, whereas in a chain and sprocket system, the chain is usually a metal chain. You'll notice on our final robot here, for this roller intake, a lot of pulleys are used to transfer rotation from the motor to the intake wheels. One thing to point out is that the pulleys are represented, but not the belts. VersaBlock are basically attachments to 1x2 stock that simply house a shaft. So commonly they're used on drivetrains. As you'll notice in the final robot, a VersaBlock, which is right there, houses the shaft that goes through a hole in the 1x2 stock, and which attaches to the wheel. The ultimate purpose of a VersaBlock is to reduce the friction between the shaft and the rest of the robot, so that the shaft can spin freely inside the bearing and reduce any. An important thing to point out is that the orientation of the VersaBlock on the stock changes the height of the hole. So you'll notice at the center wheel that there is no flat surface of the VersaBlock, whereas at the ends, the VersaBlock has the flat side on top. When the VersaBlock is oriented such that the flat side is on the bottom, such as over here, and the ridges are on the top, the center of the hole in the VersaBlock is a bit lower than if the VersaBlock were oriented the other way. So this means that overall, on the drivetrain, the center wheel is a bit lower than the other wheels. And really the main reason for this is that having the wheel have a center drop makes it easier to turn and reduces the friction experienced on the ground. Wheels have many different purposes in FRC, from uses on the drivetrain, on rollers, or on grippers, and many other mechanisms. There are many different types of wheels which serve different purposes. This, for instance, is a traction wheel, which is a drive wheel. It's what is used for the robot to roll around. So you'll notice on our robot, we have 4 traction wheels. Another type of drive wheel is the mecanum wheel, as well as the omni wheel, which are wheels that let the robot move in multiple directions. You'll notice on the omni wheel that from this angle, it looks like a regular wheel and it can roll around, but these gray parts are also little rollers themselves that can roll sideways. Mecanum wheels are similar in that these little gray pieces can roll independently, which allows for a robot that uses mecanum wheels on its drive base to rotate in to move in many different directions. There are also wheels that are used specifically for mechanisms, such as hex wheels and flex wheels, where a big portion of the wheel is rubber that can twist and bend. So for our robot, we used flex wheels on this roller intake, which would take in the ball cargo. We used flex wheels because they could compress themselves to accommodate for the ball getting intaked and squished. The pneumatic system of the robot is an air-powered system that allows for movement of parts. This is a piston, which is a part of the pneumatic system. It's a tube that, when filled with air, the shaft here can expand, which allows for linear motion. And for instance, on our final robot, these 2 pistons here, when they're filled with air, this allows this wheel setup to drop down and lift our robot up. In addition, some other parts of the pneumatic system include the compressor, air tanks, and gauges, pressure gauges. Electronics are used to power different parts of the robot. Some electronic components include the power distribution panel, the RoboRio, the radio, the voltage regulator module, the pneumatics control module, the main circuit breaker, the battery, and the motor driver talons. Generally in CAD, we only put in the main layout of all the electrical components, but you'll notice that we skip CADing all the wiring